All right. Okay. All right. I feel like I'm talking to myself every time I do this. Welcome back to Virtual University. And here we have a picture from Matthew Sturm from Alaska. And he says that we as a class have to answer, what are we looking at? What's wrong? And how did it happen? And I did push record this.
Okay.
So just to make sure I know I'm talking to live people, can you type some ideas into the... So Devin says wind loading and wind scouring. We've got a snowdrift here. We're looking at drift. What is the fence? The wind fence is not doing its job. It's not helping. It's doing a different job than it was intended to do. Josh says, is that a snow pillow? Yeah, that was supposed to be a snow pillow. Also a precip gauge. Okay, so today what we're going to do, the first module, we're going to do class logistics. I'll talk a little bit about homework 1, and then I'll walk you through a little bit of Pangeo and Hydroshare, and hopefully everything will work virtually while I do this. Module 3.2, we'll talk about the model forcing data, what you put into your model, what you were measuring with that precip gauge behind the wind fence that we just looked at. Module 3.3, I'll then give you my personal opinion on best practices for selecting forcing data, particularly in complex terrain. If you want a textbook, I like the Snow and Climate one by Richard Armstrong. It costs $70 on Amazon, which I think is bad, but your library probably has it. If you're at the University of Washington, just wait until after the class ends, because if you request it, they will make me give it back. So where are we in the class? Last time we talked about the structure of a model, layers, and internal processes. We started homework 1. Today we're talking about meteorology. The critique of reading 1 is due. With regards to time zones and turning in your homework, don't worry about it. I get a timestamp if it says you're late, but you're within a time zone difference of where I am, or East Coast, plus or minus 3 hours. Don't worry about it. I'm fine. Get it in on the right day, and don't worry about the time zone stamp in Canvas. And then next Monday, we will talk about turbulence over snow, about the energy balance in the surface meteorology. And then next Wednesday, homework 1 is due. So I want to make sure everybody is on the same page with homework 1. So first, did anybody have any trouble with homework 1A and 1B in Hydroshare Pangeo? All right, so I am going to escape out of this, and hopefully, all right. So hopefully everybody can see my screen here, which should show a web browser with Jupyter Lab. All right. So I didn't see any chat or hear anyone talking about problems with 1A or 1B. So starting tonight, and don't worry about accessing this in real time right now. If you're already in, great. The reason some of you might have been logged in and noticed I kept randomly hitting things on it is because if you don't keep your session live, it takes a long delay to log in. So you might need to wait on the login. So where you would want to start is if you go to examples, you'll see homework 1, and then you'll see there's homework 1 ABC. I have open here on my tab homework 1C. The first thing you want to do, if you just read the directions, it says to always save it in your work directory. If you're having trouble with that from home, you can add a folder, which is this little icon right here that's highlighted. Add a new folder. I have work in there. You can have homework 1. I'm going to do class demo today. So basically, homework 1C just requires you to get everything set up. It imports data, and then you do a test run, which you can see I already did. For each of these gray boxes, you just hit Shift Return on your computer to run it. When you get to anything that says execute, here it says s.execute, you may have to wait a minute or 5 minutes. You can work on something else. Check your email while it's going. And then right after that is always a test plot to make sure you actually got output. So I can make sure I'm still live. It makes the plot again. So there's nothing difficult in homework 1C. Okay, so you get to homework 1D. And now we're talking about the snow layering schemes. And so what we're going to be doing is down here, we'll be looking at 4 different simulations. We're going to run the SUMA model with CLM 2010. That's a climate model with 5 snow layers. And that one is already programmed in for you here. So what you're doing is you start by setting up the path. I've already done this. You can just hit Shift Return in each of these gray files. You set up the path. You look at what the options are. It's just outputting the options. You're then setting the option to be CLM 2010. Again, is this one, you're creating an out file. You need to name it. There's both an object file, which is the data set, and then there's an output file, which is a netcdf file here. You also create a run suffix that labels everything with the same suffix, and you tell it it's running local. Local is local in virtual Google land, and everything will run there, not on your own computer. When you get done, you just want to check that you actually ran a model that had 5 snow layers. So this plot will give you n snow, number of layers, right here in your output file, creates this plot. Okay, so where I wanted to talk you through is where you are supposed to now do things by yourself. So go ahead and run through this part, read all of the words. I'm going a little quickly. And then when you get down here, it says, okay, now repeat what you just did, but with the Jordan 1991 option for snow layers. Examine the differences in the snow layers themselves and also how they affect other characteristics in the snowpack evolution. Everything else except the layers will be the same unless you change it explicitly. Okay, so how do you get started here? If you're not comfortable with Python, the things that I find most useful are you put a plus and that creates a cell. So now you can decide whether this cell wants to be an action item. So right now it's gray, like other things that create action items. That's the code selection up here. If you don't want to write code, you can write markdown, and then you can use it just to type something. I'm going to copy something from up above, or whatever. You type what you're doing so you can keep track of it. So what I do is you go back and you say, okay, what did Bart do when he put this together? So he had to set the decision object to CLM. So there are 2 objects here, CLM 2010, Jordan. We want to set it to the other thing. So what we can do is copy this, come down where we are here, create a new one, label it code, copy code, and then we want to make sure we've got it right. So we're going to call it Jordan 1991 and hit enter. All right, If it doesn't give you an error message, you're doing good. And you want to make sure you save it frequently. Again, remember that you should start with over here in File, Save Notebook As. So here I've got it saved in Work, Class Demo, Homework. If you opened it from the examples, it will automatically save back to the examples. The examples belong to Bart and they get overwritten regularly. So the work file belongs to you and your login, and so it will be saved. So if you are working on this and then get distracted, you can come back to it and it will have these 2 lines or whatever you entered in the Python notebook. All right, so we created our decision object. Now we add another one. We're going to do something else. We say, okay, what did he do next? Set the decision. He then ran the model. So we copy this. And what you want to notice is that he's saving it as CLM 2010. We don't want to overwrite that. We want to save it as our own. So we want to change that to Jordan 1991 at each location. We still want to run it local. And now you can see it gets boring because we have to wait. Now when it says execute, this computer that lives in Google Cloud is actually running 4 years of snow model simulations. The other thing to be aware of is Jordan is the one with 100+ snow layers. Snow models take longer to run with all those snow layers. Can I expand the screen? Makes the text bigger. Can anybody tell me how to do that? I'm happy to if somebody tells me how to do that. View, zoom in. That is a little better. View, zoom in. Is that better? Make the window as big as it can be. Okay. How's that? Yeah, okay. Please, if there's anything else that is problematic, I cannot see what you see, so make sure you give me feedback. And I am also open to people turning on their microphone and interrupting me. If you are not able to follow what I'm doing, then I'm not accomplishing my goals, so I appreciate the feedback. Okay, so what you'll see is while I was expanding my screen, the computers in the Google Cloud were working very hard, and they output that they ran the Jordan 1991 model, that it's been saved in my file, work with this horrendously long name, data contents, Reynolds settings, snow model, everything is saved there. It ran water years from 1999 to 2003. Et cetera, it did everything today, and it stopped. Okay, now, how do I check that it gave me something useful? Again, I go up to what's in the example with CLM 2010, and I see that now there's a plot for the number of layers, and we want to see if indeed we did get about 100 layers at the end of this. So again, I go somewhere here. I say I want another box. Put this. Now my subscript is no longer CLM. I named it Jordan 1991. And if I forget what I named it, I can go back. JRDN 1991. Hit Shift Enter. And number of snow layers went up to 60 in some years, and in 2002, it had the most snow layers. It went up to 100. So this was successful. Now, if I want to know how to get data out of this so that I can look at it That was in homework 1A and 1B. So similar to how I just changed the subscripts here for my model run, you should be able to go back and copy and paste from those homeworks and put them in and get the data out. So now when you get the data out, it will output it to Hydroshare, and you will have a link that says, I want to see my Hydroshare resources. The other thing is, if for some reason anyone has problems here, I shared my output in Hydroshare with everyone. So if anything happens in Jupyter Notebooks or in the cloud where you have trouble, you can also go and look at my output. So you should all be now a member of a Hydroshare group, which lets you view my files. You also have your own, and what you can do is that once you create your own files in Hydroshare, can manage who has access, and you can give the entire group access to anything you do. You can then ask other students or me to look at something that looks odd. You can put your IPython notebooks here, plotting code, anything you want, so we can share. Are there any questions on the homework or the Hydroshare? Yes. So Tim asks, I keep getting something that says PD time grouper is deprecated and will be removed. Please use PD grouper, et cetera, et cetera. You should not be worried about that. And if you read Bart's code in the examples, basically Bart's comments, there are multiple spots where he says, don't worry about this, don't worry about that. What's going on is that because Python is an open language subject to development, and because some of these codes were developed in a slightly older version of Python, it is really telling us that we should upgrade our system. We don't need to worry about this because as long as it runs, we are not worried right now about being the most up-to-date Python developers. So as long as things keep working, don't worry about it. There'll be errors in multiple of the sections, which are really about programming. I'm a MATLAB person, and it periodically tells me, like, you could do this more efficiently doing X. And as long as my first thing works, I'm happy. Any other questions? Well, as things come up, please, as you're working through this, send me an email, post on the discussion page. Feel free to use Hydroshare to share things, to get feedback. We're all working on this together, and it's a pretty new system. I'm pretty excited about it because normally it takes people like a month just to install Suma on their computer, and you guys can run it in week 1 of a class without worrying about what kind of software you have at home at all. So it's pretty exciting, but that doesn't mean it's error-proof, it's new. So anything that comes up, let us know and we'll work with you. Just a few things. You should be back to seeing a PowerPoint. Yes, excellent. Using Hydroshare, there's a little bit of etiquette to working in the cloud. Pangeo is in the Google Cloud, and it will erase everything we put there within a year. So if you clutter it up a little bit, Google probably doesn't care. They're just going to wipe us all clean. However, Hydroshare is designed to save things. So please be thoughtful in your use of it. If you are generating test data as part of the assignments and you don't need it ever again, but you just are practicing putting it in Hydroshare, push delete and get rid of it. If you have multiple versions and you don't need old versions, please delete it. The other thing is that Hydroshare offers the option of publishing all of your model output and all of your code. This is an incredibly useful thing if you're going to publish your work, if you're doing your research. And now, for example, if you're sending something to WRR, we will require you that everything is publicly available. If you've been keeping track of things in Hydroshare, this is really easy. However, please don't publish your homework for 2 reasons. One, CUAHSI actually has to pay for each DOI that it gives to people. So we don't want them to have to pay for 15 versions of the same homework assignment. And while they're really happy to publish research for paper, they don't want to publish all of our practice work. Also, once a repository is published, it can no longer be changed. And we're hoping you'll take this homework and do something else brilliant with it after the class, so keep changing it. Christina asked me to let you all know that metadata is extremely important. We don't have time in this class to go through all of the details of having good metadata, but just taking the time to enter things that will help you later of what you're doing and why will help you. So don't just skip or ignore metadata because it's boring. All right. Okay. So as you're doing your homework, here are the 4 layering schemes. The one on the left is the Jordan one that we just ran through that got up to between 60 to 100 layers of snow. Second one is CLM. The third and the fourth one will be configured from the CLM template, but basically the layers will be constrained so that CLM will never evolve more than 2 layers. And there is an example in the Jupyter notebook, and if you have questions, please let me know. I think the example that Bart put together is pretty clear. Once you get this out, you're wanting to think about what we talked about on Monday, the state equation for thermodynamics, including the heat capacity of each of the snow layers and the spatial resolution of the temperature gradient. There's a PDF on the Canvas page that will walk you through what I want you to do with the analysis. Basically, you will need to make multiple plots of your model output. There are some example codes in the IPython notebook how to do both some basic plots and how to output time series if you're not familiar with NetCDF. If you have other plotting code and can get things out of NetCDF, great. I would greatly appreciate it if everyone in the class would share their plotting code on Hydroshare so that if you found a nice way to make vertical temperature profiles in your IPython notebook, please share it with people. Again, it's a work in progress, and our goal really is to understand these model experiments and learn some coding along the way. I'm not grading you on your beautiful coding ability. However, if you impress all your friends, they will be forever grateful to you. Our goal is to use these controlled model experiments to help understand the internal workings of the snow model, specifically with regard to the layers, heat transfer through the layers, and to liquid water percolation, both aspects we talked about on Monday. Again, post questions in the discussion, and if anyone has any questions now, feel free to either type in the chat box or turn on your audio, or I even give you permission, you can turn on your video if you want. All right, I presume everyone knows exactly what we're doing, and if not, they'll tell me later. All right. So now that we know how to run a snow model, we talked about on Monday that snow modeling is a boundary value problem, and the model forcing data is absolutely critical to what happens in your snow model. So questions, if you want to model snow somewhere, where do you get model forcing data? How good are they? And what some people may be thinking is, wait, I thought I was going to be a hydrologist and not a meteorologist. Turns out you've got to do a fair bit of meteorology to be a snow scientist. This lecture, again, was put together by me, but I had help from a lot of people, including prior students of mine, Mark Rowley, Nick Wayand, Adam Mossman, Carl Lapo, Nicoletta Christia, as well as Martin and Bart, who you've heard me mention many times as the key SUMA developers. All right. So thinking about our boundary value problem of the snowpack, right? That the surface is prescribed in the model as the net energy balance. So what do we need to know as part of the net energy balance? You've probably seen a graphic like this somewhere in some prior class, right? The energy balance at the surface is a function of the incoming solar radiation, some of which is absorbed by the atmosphere, some is reflected by clouds, and some is reflected by the surface. And we'll be concerned about the snow albedo, and we'll talk about that on Monday. There's also incoming long wave radiation, which is coming primarily from clouds and water vapor, as well as greenhouse gases in the atmosphere. There's also outgoing long wave radiation. So these numbers here are approximately in watts per meter squared, the sizes of these averaged over the globe. And what you can notice is that the incoming long wave radiation that reaches the surface is in general greater than the incoming shortwave radiation on average. However, so much long wave is emitted from the surface that in net, the net shortwave is generally greater than the net long wave. We will also on Monday talk about sensible and latent heat flux, which need to be resolved in terms of boundary layer meteorology and parameterizing turbulence at the surface, and we'll get there Monday. So all of these are outside of the boundary of what we're modeling, which means we need to go find something else, either an observation or somebody else's model. One thing, this is a slide that Mark Rowley put together that we need to consider very carefully in terms of our forcing data is the garbage in, garbage out paradigm, where if you have garbage in your forcing data, no matter how perfect your model is, your results will be garbage. Similarly, if you have perfect forcing data in a garbage model, your results are still garbage. The thing that you need to be careful about is the word you will often heard buzz term is equifinality, in that hydrology is amazingly unique in the ability for two wrongs to make a right. You can have garbage in two components and get results that look really good. So you want to be careful in your detective skills to avoid the garbage plus garbage looks wonderful. We really want the holy grail, which is the bottom down here of all of the amazing forcings, models, and results. All right, so the outline for this module is to answer the following questions. So at a point, what do we need to force the model and how are these measured? At a point, what do we do if we're missing some of the variables that we need to force the model? How do we distribute data spatially if we need to go somewhere we don't have a weather station? If you have data, how do you make a forcing file for this specific model so it can read it? And if you're interested in climate sensitivity, what can you do? So at a point, what do we need to force the model and how are these measured? So this, Mark Rowley put this together, and this is the anatomy of an ideal mountain weather station. So raise your hand if you've had the joys of installing or putting something on a mountain weather station. Looks like about half the class. All right, for the half the class that has not had the benefit of going to their own mountain weather station, your ideal weather station for measuring snow has a snow pillow at it, which is going to measure SWE, or snow water equivalent. What Mark has highlighted here is the blue is something we primarily use for model evaluation, which we'll get to later in the class. And the yellow is something that we primarily use for model forcing. A snow pillow is essentially like a truck weight that just weighs the weight of the snow, and thus it knows how much water is in it, or the water equivalent. The ideal sensor station also has a snow depth sensor, an air temperature sensor, a precipitation gauge that has some kind of windshield so that you don't get too much undercatch in it, a wind sensor. This is a picture of an anemometer with a wind vane that primarily will give you wind speed and direction. A relative humidity sensor. Mark has drawn these as two separate ones, but you'll often see them put together within the same housing on a weather station, as well as radiometers. So this shows pyranometers, a pointing up pyranometer, which measures incoming shortwave solar irradiance, as well as a downward pointing pyranometer, which measures your reflected solar radiation or your albedo. This may be used for either model forcing or evaluation, is why it's in 2 colors. And then pure geometers, where the upward pointing one is measuring your incoming long wave irradiance, and your downward pointing one is measuring the outgoing long wave irradiance from the snowpack, which is a function of the snow surface temperature. You may also have, this is a surface temperature, and this one's an apogee point radiometer, and it's measuring the skin temperature of the surface. Again, the blue ones are typically used for model evaluation. All right, so now we have a little animation. Here's the snow depth sensor. Has a footprint, so it measures one spot. Its footprint is generally part of the overall footprint of where water content is measured. So if there's variation, there can be issues in calculating the density from the two. You can see there's snow coming in from the sky. And then here's your both direct and diffuse shortwave radiation, which depending on your model may be measured together or separately. That is then reflected off the snow surface as a function of the snow albedo, which is measured by the downward pointing radiometer. And then you have your atmospheric terrestrial long wave radiation and your upwelling long wave radiation, which are functions of the emissivity of the snow as well as the surface temperature of the snow. Turbulent fluxes, which we will go in, and they fly in several times because they're so cool, will measure the sensible and latent heat exchange. And this is in general a function of the wind speed as well as the profile and curvature of the wind speed over the snow surface. And we'll discuss this more on Monday, as well as the surface temperature of the snow and the vapor pressure in the atmosphere. All of this together gives us our surface forcing for our snow model, which is what we talked about in the internal energy. So that's du dt, the internal energy of the snowpack, which is the sum of all of the temperature and moisture content phase changes within the snowpack, is a function of the net shortwave radiation plus the net long wave radiation plus any heat carried by the precipitation. For example, if you have very warm rain falling on a snowpack, it contains some heat capacity. Any ground heat flux, which is from if you have warm temperatures in the ground layer, as well as turbulent heat fluxes and change in state. This is the melt energy, which is drawn as a minus as it's generally leaving the snowpack as the water goes away. All right, so this was our animation of the perfect weather station. So Mark Rowley also put together 2 uncertainty scenarios for reference. Just how good is the perfect weather station? So one thing you can do is you can look up, what are all of the instruments that I put on my weather station? And you can look up in their manuals what their uncertainty range. And you'll find very quickly that that solar radiometers are only good to plus or minus 5%. Precipitation sensors in a lab are good to plus or minus 3%. What you will then find is that if you look at analyses that have been done not in a lab calibration facility, but in people looking at instruments that were actually left outside for the winter in the snow, that your uncertainty and your errors get substantially worse. By far, the greatest increase is in precipitation, which in a manufacturer sense is plus or minus 3%. That's basically the ability for the tipping bucket to handle water if it was poured in carefully. In reality, we'll talk about this a little bit later today, the uncertainty range is plus or minus 75%, if not worse, by a number of citations. You also see that the accuracy of most radiometers is worse than 5%, even the manufacturer specified accuracy if you buy a radiometer that is not the most expensive and top of the line. So be thoughtful about how good your observations are. All right, the next thing, given that instruments left out in the wild are not as well behaved as instruments kept in a lab, what can you do? All right, so always plot and check your data. So we are going to play what's wrong with this picture. So get ready to type in your chat box or turn on your audio and talk. And for now, I'm going to pick on solar radiation sensors, which are pyranometers, just because they're easy to pick on. Okay. All right, so what is wrong with this picture? What I'm showing you is this is year on the bottom, and this is a pyranometer or a solar radiation sensor that was at the Tuolumne snow pillow in Yosemite National Park in California. This is the measured shortwave flux, and the red line is the theoretical maximum flux we would expect from the top of the atmosphere. So the chat says our problem is after 2009, something went terribly wrong here. It's just observing more solar radiation that is possible. You guys got it. All right, let's see if you can get the next one. All right, so now this is solar radiation from the Alptal site, which was part of the second snow modeling intercomparison project, which was called SNOMIP2. And we are looking now at a number of days in December in water year 2003 to 2004. Again, we are looking at the potential maximum top of the atmosphere radiation as well as the observed radiation. So what is going on here? So Michelle says there's a ridiculously low observation between the 22nd and 23rd. Could have been an incredibly cloudy day and snowing really hard. That day could be snow accumulation on the pyranometer. That one I didn't think was the worst. There's some other things here. Jonathan says maybe there's a consistent gradual decline. That too I'm not worried about because we're only looking at a week. It may have just gotten cloudier over the course of the week. So that one doesn't bother me so much. All those circle points. Yeah, the circle points, I circled them for a reason. What about those circle points? Yeah, so again, like the prior one, they're out of bounds of the top of the atmosphere. There's also something, Justin says maybe a shadow crosses. That's potentially the timing could be wrong. Yeah, Stephen picked up, if you notice, look right here at sunrise each day, that the observed radiation seems to rise before we're calculating that it's theoretically possible. One of the reasons why I plot this and why it's very relevant to snow modeling is that Martin's SUMA model does a preliminary check of the data you feed it. And if you feed it solar radiation data that exceeds the top of the atmosphere at any time of day, the model will stop and tell you it is not going to proceed. And so a common problem, this is particularly a problem with daylight savings time, is that timestamps of some instruments adjust to daylight savings time, while timestamps of other instruments do not adjust to daylight savings time. And if you are calculating your potential top of the atmosphere solar radiation in one time zone and you're observed in a different one or by a different hour, you can just get offsets in the timing. California is going to vote to get rid of daylight savings. It will make all the scientists happier. That's excellent news. But for the meantime, we also have historic data that sometimes was and was not in daylight savings. Also, sometimes things don't adjust to daylight savings, but we're programmed in either standard time or daylight time without a shift. So just double check. Radiation is the best way to actually figure out the timestamp in your data. If you are running an hourly model, this is important. The other case where it becomes important to snow is if you are doing something where you calculate shading, for example, shading due to slopes, and east and west facing slopes can have serious biases if your solar radiation data set is offset by an hour in the wrong direction. I won't go into this, but it's worth checking. Okay, so now here's one where the timestamp is okay. This was all less than the theoretical possible at top of the atmosphere. It's in Snoqualmie Pass, Washington, in February, where we generally are less than the theoretical at the top of the atmosphere by quite a bit. But there is a problem here. What do you see as the problem? The blue line is downwelling shortwave radiation, and the green line is upwelling shortwave radiation. See, a number of people are noting that on the 23rd and the 24th, the upwelling is greater than the downwelling, right? That should not happen unless your radiometer looks like this, right? So very common thing with radiometers left out in the snow zone is your snow will pile on top of your upward looking pyranometer or pyrgeometer, and there'll be no snow on your downward looking sensors. So another thing to check if you have both upwelling and downwelling is to flag cases where it doesn't match. I will, there's actually a GitHub repository that Carl Lapo put together that goes through all of these checks for solar radiometers that I will give you guys a link to if it's helpful in your future work. All right, so now here are 3 days in June 2005 from 3 shortwave radiometers that were put out as raw stations in Yosemite National Park, California. So what's wrong in this picture? Justin says shading. Yeah. The raw stations are for forest science, and so they like to put their weather stations near, around, or somewhat under trees. And these are actually branches from surrounding trees that shade the radiometers at certain times of the day. Another thing to be aware of is that even if somebody went out and very thoughtfully put out the radiometers 20 years ago and they weren't shaded by a tree, if a tree grew, it can start shading your radiometer. And if you suddenly, clouds don't usually go over at the exact same time every single day. So again, check for weird patterns that might be related to things around your weather station shading it. All right, so we just found that we had to throw out a lot of our data, right? So what do we do if we're missing some observations? The thing with modeling is, again, the model requires that you prescribe boundary conditions to it. SUMA does not consider it its model responsibility to generate metadata. You have to do that first and then give it the model. So what can you do? This is from Mark, and I think it sums it up in that we showed the picture of the ideal snow station. The ideal snow station is elusive. These are 1,318 weather stations measuring snow in the Western United States. And of all of these, you can see that, shortwave and long wave, the radiation energy balance is only measured at a very small fraction of them. Radiation is the least measured, and the majority of weather stations just have 2 measurements. Most have temperature and precipitation and not anything else. It's understandable that they wouldn't measure radiation due to just the problems of maintaining the instruments in remote locations. And so, there's some debate about, whether a crappy measurement is any better or worse than no measurement at all. Here is a picture of the Western United States from Mark's analysis, where he found those stations that actually had 6 to 8 instruments on them. This does not refer to how often they were calibrated, checked, or anything else, but there at least is some measurement of this made. Again, the black dots are most stations. The white dots also have a little bit more. often wind speed or relative humidity, and then the red ones actually have more data to conduct an analysis. All right. So something to realize when you look at this is that physically based snow models are significantly limited by the availability of forcing data. Again, we go back to the garbage in, garbage out paradigm. If we're not able to come up with good data for our models, we are not going to be able to do much. So, here's a picture of the weather station that the model needs. And here's a case one of what we typically have, right? No data at all. And, that's a problem. Case two might be you have one of those more common snow stations that measures temperature and snow and precipitation, but has nothing about wind, radiation, or humidity. So you still have to come up with something to get your forcing data to run your snow model. So what we often use are either empirical methods where we try to estimate these. For example, the mountain climb model of shortwave radiation takes the daily temperature range to estimate atmospheric transmissivity to estimate incoming shortwave radiation, with the idea that if it's a clear night, lots of radiation at night, and you have a very low minimum temperature, and then the sun comes out the next day and you have a really high maximum temperature. And so that gives you an idea of cloudiness and hence shortwave radiation. Other methods include spatial interpolation from other stations you might have, using output from a mesoscale weather model, basically take another model and couple it with your hydrology model, or getting data from satellites. And when we get to the best practices, I will talk through some of these. In terms of some example empirical methods for estimating point missing forcing in terms of hourly data. This is a slide, again, put together from Mark Rowley that gives you a starting point. I find a lot of people starting snow modeling, the first thing is, oh my gosh, the model won't run because I don't have any good forcing data. For air temperature, you will also find that there are more frequently measurements of daily values of Tmax and Tmin than hourly temperature. So you can fit geometric curves that assume there's a sinusoid. Precipitation, if you only measure that daily and you want hourly data, the most common method employed is just assume that precipitation fell hourly over the day. So you want hourly forcing and you measured, 24 millimeters of precipitation. That's a monster flood. You just divide it by 24 and get 1 millimeter per hour. Wind speed is a remarkably difficult thing to measure in the mountains. In the snow, your wind sensors tend to freeze and not work. Most commonly, people will either assume that wind speed is 2 meters per second everywhere in their domain all the time. We know that's not true, but your model generally won't crash if you tell it that. Or people will interpolate from 6 hourly 2.5 degree NCEP NCAR reanalysis data. Why? We just haven't come up with anything better so far. Relative humidity, the most common thing, again, is to assume that the minimum temperature equals the dew point temperature. The concept behind this is that temperature cools at night until it gets to the dew point, and then water starts condensing on things, and that's the point where temperature stops cooling at night. This can be problematic in regions with really low humidity because Tmin might never reach the dew point temperature. But for most areas, you can use this to calculate relative humidity from the vapor pressure, assuming Tmin equals T dew point. Scherefeld published a paper in 2013 where she found similar performance to the running it all method using the Kimball method, which was easier to implement. Again, relative humidity can be estimated just from the air temperature. Shortwave, as I gave the example, looks at the daily transmissivity from the temperature range. Ted Bone in 2013 did a nice study of the accuracy of this approach. And then long wave is calculated empirically, and it's Mark recommends the Dilly, O'Brien, Unsworth, and Monteith based on a study by Flershinger et al. In 2009, which evaluated a lot of empirical methods for long-wave radiation. All right, so we've now made up a lot of data at a point, but now we suddenly have to go somewhere else. So how do we distribute data spatially to locations without weather stations? So again, this is kind of a laundry list, how to go about what are your distributed foreseen data options. One is to use output from a numerical weather model, such as WRF. Wayand et al. 2013 is an example of how that was done. Preferably, you want WRF run at a fairly high resolution. You can use satellite data. Satellite data is really good at giving you the radiation values, incoming radiation, cloud cover, surface temperature, and land cover. You can also use a gridded product that was produced by someone else. However, I would recommend doing this with care. You want to know, how did this person produce their gridded product, and how well do you trust their methods for the gridded product? Common one is an LDAS2. Here's a link to it if you want to check it out. Another option are hydroclimate forcing data sets. Some were put together by Ben Livna or Ed Maurer or Alan Hamlet, who all worked at the University of Washington. Their data is available. DAMET was developed independently, was also available. One thing to know about the Livna and Maurer data sets is that they all assumed a temperature lapse rate of -6.5 degrees Celsius per kilometer, which is correct on average over the globe, but is wrong in many specific individual locations. So double check their temperature. You can also use local station data and knowledge of the terrain to empirically distribute the data yourself. Prism by Chris Daly is one of the most popular products. Is available. TopoRad is developed at Boise State. Mountain Meteorology is a software package developed by Glenn Liston and Kelly Elder that will distribute station data for you. Depending on the scale at which you want to run your snow model or your point model, you may still need to downscale these products even after you get them. You can also, in addition to these, look at NSIDC, the Snow and Ice Data Center. You can look at all of their data products, and here's just an example of what you get if you search on snow. You can get data set of snow water extent and look at what you might want. They have less met data there and more data that might be better for model evaluation. All right. So again, if you decide you want to distribute the forcing data or further downscale your data in complex terrain, what can you do? Again, there's no exam on this, but I want you all to have the material to go back to it for reference if you need it. Air temperature is typically a lapse rate relative to elevation. This is either fit to longer term spatial data or developed with the standard atmospheric lapse rate of -6.5 C per kilometer. As I just mentioned, the standard lapse rate is often not the best choice. For the Pacific Northwest, -5 is a much better number, and Minder et al. 2010 went into the details of that. Prism, WRF, and atmospheric soundings, which are weather balloons let off, all came up with very reasonable values for different regions that were better guesses than just assuming -6.5. Precipitation, spatial patterns derived from a numerical weather model or best fit to multiple stations over a long time period. I'll show you a bit more about pros and cons of these two choices should you use a weather model versus a gridded data product. Again, the most common product for precipitation used in the Western US is Prism. There are some issues both with storms that don't follow climatology as well as with areas that just didn't have a lot of precip just to start with. Wind speed, some of the methods for downscaling reanalysis data were developed by Adam Winstrol in 2013 or by Liston and Elder in 2006. Both consider topography and specific influences on wind and snow for distributions. You can also use wind from a higher resolution atmospheric model. Many of these are still work in progress and under development. So if you need good wind data, let me know if you figure out the best way to do it, because that would help me as well. Relative humidity is often assumed constant with elevation. Again, if you want to look at an evaluation of the pros and cons, how good that is, Schoenfeld in 2013 examined multiple methods. Shortwave irradiance, typical techniques are to adjust for topographic slope, aspect, and shading from surrounding terrain. Some people also adjust for variability in clouds. Carl Ritger's PhD thesis has a really nice explanation of this. His PhD thesis is housed at the UC Santa Barbara, if you want to look it up. It is incorporated in a lot of snow and hydrologic models run at high resolution. This is not directly implemented in the SUA model we will be using. So if you are trying to model a location that has shading, you need to pre-process your shortwave radiation based on slope and aspect. Similarly, incoming long wave radiation needs to be adjusted for elevation. Basically, there's less incoming long wave at higher elevations because there's less moisture above you in the atmosphere. You also might, particularly if you're under trees, want to adjust for the sky view factor. How much of the open sky can you see versus mountains next to you or terrain? A rule of thumb is Marty et al. 2002, which they suggest decreasing the long wave by 30 watts per meter squared per kilometer. So if you get something that is distributed but is not as high a resolution as you would like, an example from Nick Wayand's 2013 paper would be you could use 6-kilometer WRF output as input to a 150 meter resolution snow model. Obviously, you could change those numbers as you like. Is that you pick the point in your snow model and then just do inverse distance weighting within these. There are more sophisticated ways of doing this, but in general, by 6 kilometers, you have resolved the majority of the precipitation variability in the terrain, and then your downscaling can be best guess. For temperature, which has a more known elevation dependence, you should first adjust for the altitude difference between the mean 6-kilometer elevation location and the elevation of the 150 meter grid cell of interest. In this case, Nick Wayand was working in California, which does follow the negative 6.5 degrees C per kilometer lapse rate. And so after you adjust everything in temperature land to a constant elevation surface, then you use the inverse distance weighting to average. Again, we won't be modeling this, but I want people to have all of the background, because once you start trying to move any modeling to the real world, these techniques become really useful. All right, here is a picture of how you can use a digital elevation model, or DEM, to determine the potential solar illumination at all times of day and times of year. Basically, you start with a potential radiation, where there's a lot of code available to calculate that. Then you come up with some way to determine transmissivity. And finally, you figure out the solar geometry. This was a graphic in the upper right-hand corner that I put together trying to figure out what all the angles were relative to the sun on a flat versus slope, where you see here there's the zenith angle of how the sun varies as it moves across the sky, as well as the azimuth angle, which describes as it moves from west to east. Zenith is how high it is above the horizon. And then your slope will also vary from a flat surface, which will then have angles to the sun. In addition to just your geometry exercise, which is something that is known, it's all physically known, but it's very easy to make coding mistakes while you do it, so be very careful. We once had a version of the DHSVM model that was consistently making the sun rise in the west and set in the east, and that gave some odd snow results on west versus east facing slopes. It was somebody just put a minus sign in the wrong place. Fewer models actually include diffuse radiation from other mountains around, as well as something you might or might not want is as shown here in figure 1 from WN 1994, is while most things will calculate the local slope and its influence on solar radiation, you may have higher peaks around. And so some models, including TopoRad, which was developed by Jeff Dozier's group and is described, part of its development is described in this paper, will include shading from other mountains. For example, you can see that when the sun is in the upper right-hand corner, that this mountain by the number 3 is going to shade a lot of this location on the smaller mountain over here. All right, so now you've got your data and you fixed it and you made it perfect. So now you want to run your snow model. All right, so we've got the SUMA model. How do you make a forcing file for this specific model? So SUMA reads in netcdf files for the meteorology. Due to the short time frame of this class, we have prepared all of the meteorological files you will need for your homework assignments. So, so if you're feeling overwhelmed, you don't need to worry about this. However, in the future, if you want to use this model, you may want to model your own favorite sites. Most people do. So details on how to prepare your netcdf file can be found on the Read the Docs page, which I have the link here. The link is also available in the homework notebooks on Pangeo. Each forcing file must have a time dimension, so you have to have a constant time step for everything, and an HRU dimension. For point modeling, which is what we're discussing, you only need one HRU dimension. We are just, a point is one HRU. HRU stands for hydrologic response unit. So if you are using SUMA as a hydrology model, you likely will want multiple different response units that would all be accumulated in some way for stream flow. That's beyond the scope of this class, so you could just make it be dimension 1. That's what will be used in most of our homework, but be aware you can do that and it must be defined. The variables that you need are defined in this table. And what I want you to really note about these variables are the units. The data you download when you go and you do your search for all your forcing data, you will find all kinds of odd units. Maybe hard to know what the units are. Always check the units and always check what your model expects. The number one problem with modeling, besides I can't get it to compile and turn on, is feeding your model for the wrong forcing data, and often the wrong forcing data in the wrong units. So always check the units. Make sure you realize that you need wind speed at the model forcing height. If you're measuring wind speed from some WRF model that's 2 kilometers up in the atmosphere, that's probably not at that height. So you probably need to adjust it before you put it there. You also will find that you can get data from a lot of weather stations that don't tell you what height things are at. So you may want to guess this or get a picture and look at that. Again, air temperature is in Kelvin, not degrees C, etc. Just remember units. You will also need to have an ASCII file naming your forcing files. This is in the code. And you will need to describe your site. This is called a local attributes file. It's also in netcdf format. Details are here. And you'll need to know latitude, longitude, elevation, slope, vegetation type, soil type. This matters a bit for the ground heat flux. If you're not sure, you can generally guess something reasonable as long as you don't say you're in a parking lot when you're not. Measurement height above bare ground. This is critical for the turbulence calculations, even though sometimes you may not know it at all your sites. And also, as I mentioned before, SUMA will ask you for an HRU and routing info. If you are doing a point simulation and only want to look at snow output, you can make these up, but you do need to put something there or the model just won't run. In terms of pre-processing code, what we've been using in our workbooks is PySumma. It's under development, and so it's getting better all the time, but it's not done yet. So you can use the PySumma code to help with some of the pre-processing and model decisions, but realize that it is still a work in progress. So I will share what I have, but right now my files all read text. The prior version of Summa all read text files, so I need to update them. So I will post them once I have them actually making things into NetCDF. Again, because it's not needed for your homework, you probably won't want them till the end of the class. The other thing about my code is that I'm really good at MATLAB and not so good at Python. So if anyone creates anything that works better than mine, put it on Hydroshare and everyone will be happy. Make sure you convert your units to the units required by the model. Sounds like I shouldn't have to say it, but I have to remind myself. Make sure you fill in any missing values. The model will not run without a complete meteorological forcing time series. So unlike Glenn Liston's snow model, which has another model that makes meteorology, you need to pick your model that will fix your meteorology before running this model. And then you can estimate values for any term that you don't have. For example, in terms of snow modeling, the key thing is to get your pressure about right for the atmospheric level you're at. Getting pressure fluctuations does not impact the snow very much. So you can assume a constant pressure based on your altitude, and Wikipedia has some code about what pressure should be, what's the typical atmospheric pressure with altitude. All right, I feel like I've been talking for a very long time. Are there any questions so far? Everything good? I said it's not on the homework, so you guys are all happy, right? Or sleeping? Okay. All right. So the other thing that I get a frequent questions about, Scout's happy. Excellent. Glad somebody is. All right. I'm interested in climate sensitivity. So what do I do? All right. So you could downscale a GCM, which is another class. We don't want to do that. But for snow, one of the questions that comes up very frequently is, how sensitive is my snowpack in this spot to just warming temperature? I just want a baseline change in temperature and want to know about what might happen to my snowpack. So for an example, I want to test +2 degrees C. So I take a line of my temperature in my model forcing code and I just add 2. So in the chat box, am I done or have I missed something? And if I missed something, type what I missed. So Lewis says I missed feedbacks. I'm not sure what that means. What else should I do? Incoming shortwave, humidity, other MET changes related to the temperature increase. There'll be other processes. I think you're all exactly on the right track. And I think the things we need to work through are some processes our snow model will explicitly represent, right? If we change the +2 in the forcing file, it will change it. However, because we have this physically based model that uses all of the different lines of code of input, we need to take care of other things. So what atmospheric processes, as Joran wrote, what MET changes will change due to temperature changes. So things to consider for a delta T experiment. And so the ones I've highlighted in yellow, the things that you need to change. So precipitation, you can do your own precipitation sensitivity experiment, but the simplest is to just assume it's the same in the historic data set. Basically, if you look at all of the climate model runs, nobody has given me a solid answer yet of how precipitation is going to change in the future. Wind speed, leave it the same. We weren't really very good at it in current time periods. There's also no evidence that wind is going to change with temperature. Shortwave, unless cloudiness changes, we can assume shortwave is the same, unless you want to model something where atmospheric transmissivity is going to go up and down, or you think there's pollution or cloudiness changes. Otherwise, leave that the same. We can assume that relative humidity stays the same, but note that atmospheric water content is a function of both relative humidity and temperature. So you want to look at the variables for your model and make sure, if it's asking for atmospheric water content or vapor pressure, that you adjust both relative humidity and temperature. Warmer air can hold more moisture, so even if you assume relative humidity is the same, the input water content is likely to change. The big one that you need to make sure you change is the incoming long wave radiation, right? This is global warming, right? Long wave is a function of temperature to the fourth, so this must be changed. So you must estimate long wave radiation. You have to estimate long wave radiation as a function of temperature to do a delta T experiment. What I would recommend is that you find a methodology that, if you have long wave observations during your observed period for your region of interest, find an empirical method. Again, the Flerschinger paper that the references earlier has a lot of empirical options, and then use that based on temperature and relative humidity to estimate the long wave radiation. Justin says you might also want to change rain versus snow, which generally is parameterized as a function of relative humidity and temperature. In our model as set up, it is partitioning your incoming precipitation as a function of temperature. So the model will do that. You don't have to do that in the preprocessor. But if you're changing it, then definitely, if you're inputting snow and rain separately, you should update snow and rain. All right. So that is the end of module 3.2. While I open 3.3 for the last part of the class, and I have been kicked off of Jupyter Notebook because I didn't catch it long enough. That's okay. Are there any more questions about either meteorology data or homework? All right. So Justin's question about rain versus snow is a great transition to this slide, which is my favorite wintry mix slide. It's actually a picture that was from Nora Knit's website. I guess she was looking out her window and knitting. It was one of those days where you just don't really want to go outside because it's snowy and rainy all at once. Okay, so because there's a lot of material today, and again, I've given you some reference sheets and notebooks for forcing data. If I don't make it through this entire module, I'm going to start with my take-home message, which are Jessica's rules of thumb. These are based on my experience working in the Western US mountains. I'm going to show you some supporting evidence, but first and foremost, take this with a grain of salt. It's my opinion, and it's up to you to decide whether you trust my opinion or you want to do something else. So the most common source of snow model air, and this is just in summary of what we're going to show, is precipitation. In remote snowy regions, precipitation is extremely hard to measure. Personally, I would recommend using a high resolution, and by that I mean run at finer than 9-kilometer scale resolution, atmospheric model for precipitation, both the amount and the phase. So even though our model can partition rain and snow, I would directly take the rain and snow fractions out of the atmospheric model, because our evidence, and these are the paper citations that show it, have shown that the atmospheric models are better than the hydrologic models at partitioning rain and snow. I also recommend the atmospheric models over a gridded precipitation data set because of multiple papers published by Brian Henn that showed gridded data sets have a lot of problems. In terms of temperature, I would either use the temperature from the atmospheric model or from PRISM. I would not use the LIVNA data set because it's wrong in the Pacific Northwest, and I live here. So again, that's my opinion. If you're somewhere where it works great, go right ahead. For radiation, I would use CERES. This is a satellite instrument on MODIS, based on work by Laura Hinkleman evaluating it. Or I would use the mountain climb, which is an empirical model for generating radiation. It was evaluated by Ted Bone for both incoming shortwave and long wave radiation. I would be sure to lapse the long wave with elevation. Again, it decreases with elevation, and I would incorporate topographic shading in the shortwave. WRF radiation data has not looked great in current analyses. Relative humidity is less critical. While we analyzed that, it doesn't impact most snow models very much. So I would probably use the mountain climb method or whatever was easiest. Wind is a problem, but I have no idea on the good solution right now. So again, tell everyone if you come up with that answer. All right, so now in the last 10 minutes of class, here's a bit of supporting evidence, and if you have questions, feel free to post them. So thinking about what data we should use for a snow model, we want to think again about what part of the snow model are we most concerned about getting right for our given application, and then focus our energy on making sure that we have the best forcing data for that process. So right here, this is output from the SUMA model. This was run by Nick Wayand. You can tell this one was run with 100+ layers of snow, and the colors are showing the evolution of snow density, where green is higher. With 100 layers, you can make really beautiful plots. So we can divide the year into snow accumulation is the first part of the year, a time where not much is happening in the spring, where things are dominated by the energy balance and the snow temperature, and then a time in the later spring and summer where the snow is melting and disappearing. And the stream flow plotted at the bottom starts going up when that snow starts melting and disappearing. So for most purposes, snow accumulation is the most important process. How much snow accumulates on the landscape is going to determine the total volume of runoff from the snow, how much water you get. So for most applications, this is the critical thing to get right. Depends primarily on precipitation and secondarily on wind and snow drifting. So Mark Rowley, in addition to making those super cool slides we just looked at, also published 2 papers, the reference to the lower right-hand corner, where he asked the questions of what forcing data really matters to model the snow? Where should we pay attention? And he searched for the elusive weather station that had all the data. And here's Col de Port, which you saw discussed last time. Col de Port has beautiful data and shows up frequently. Here is Reynolds Mountain East, which we're using for our assignments, again, because it has nice data. Senator Beck, which also has nice data, and then Imnaviet Creek up in Alaska, which has good data for Alaska. Okay. So what Mark Rowley found was that precipitation and wind redistribution explain most of the snow season. So what you're looking at here for these 4 sites, the black are the observations. The gray are multiple models run with perturbing all the observations one by one, where he basically left out long wave and estimated, left out short wave and estimated, etc. Modeled in the red with all in situ observations, and then modeled in the blue where he estimated everything except for temperature and precipitation. So what does this really show us? The first thing is that at the warmer sites, just measuring precipitation, which is snowfall, it does a pretty good job at getting SWE. So he perturbed all the melt forcing. He added errors as you would expect and found that as long as you measured precipitation, you did okay. However, at places in Alaska and Colorado with colder, lighter snow, undercatch and wind distribution really caused more problems in getting the precipitation right. And here we return to our photo from the beginning of today. This is Matthew's photo of Mark's ideal Alaska tundra site. And this is measuring the snow. And so we're not sure if our validation is exactly right with our wind drift. It's really hard to measure snow and precipitation in an Arctic environment. All right. At most sites, if we got accumulation right, even if we had our melt forcing wrong, perturbed by those errors we showed you, then it still doesn't look that bad in terms of a snow model. The exception really is in the Alpine site, which had quite a deep snowpack, and where the errors were quite substantial in when the snow actually melted out at Senator Bend. But at most sites, if you got accumulation, the model's okay at melt. We just need to know how much accumulated. Once you've got that, now the midwinter energy balance, and you'll be looking at some of this for your homework this week. The evolution of the snow temperature in the snowpack will determine whether midwinter melt can occur and the onset of stream flow, which is shown here. Here's an example of our physically based model. As long as you give your model very accurate meteorological forcing data, most models will behave well in most situations. However, the surface energy balance is hard to come by. And you can really see this in Mark's model simulations, where the greatest divergence in all his models in terms of snow water equivalent is really when melt turns on. And you will see in your homework assignment, I ask you, when in the year do you see differences between our different model structures? Given the published evidence, I would suggest looking about when melt is about to turn on. What is that first melt in the season is generally a very sensitive thing. You can see that the models really diverge in Colorado right about March, where some of them melt quite a bit and some of them don't melt. They're still cold enough, they're not ready to turn on. In Coldeport, you see a few really diverge and start melting early. And you see the models also group into two groups based on some event here in April. You can also see the Idaho Prairie, which this is your Rennell Mountain East, this is your data set. And Mark would suggest you should look in mid-March to see if something different happens. Okay, we will talk on Monday about what we can see in the snow surface temperature. You will plot this as your homework, and we'll be looking at, you know, we talked about on Monday that the bottom is often isothermal near zero during the melt season. Again, orange here, this is a plot of snow temperature, snow depth versus time. During the melt season, it's isothermal, but again, this turning on period, when the onset of melt starts, is when these, you know, cold, which starts from the top of the snowpack, how much the cold propagates within the snowpack and when it warms up again becomes important in an onset of snow or a rain on snow event. Again, we'll talk about this more next week. So Mark Raleigh concluded that precipitation was by far the most important variable. He also concluded that long wave radiation was second and short wave radiation was third. People often ask me why precipitation is so critical. Why do I recommend it? I have some more slides, but given our time, I'd like to allow time for questions. So if you're interested in why, at the front I said use a model for precipitation instead of observations, here's a teaser. This is from Roy Rasmussen, showing all of our gauges of snow and variations by a factor of 2. These are all gauges that were put next to each other in Colorado. It's incredibly hard to measure. And so this is one of the greatest challenges. But I'm going to stop talking and open it up for any questions, comments, chat box typing. You can all turn on your video and wave if you want.
So I don't have any questions at this time, but I'm sure as I work through the homework, some will arise.
Mhm.
So hopefully I can just reference the recording of this lecture to work through any of the problems that I come across.
The recording should be available. Also, we have multiple online chat platforms. You can chat in the Canvas site, has a discussion place. You can also post comments within the Hydroshare shared files. You can also, if you probably still see my screen here, within any of your files, you should be able to, if you have some notebook or something you want someone to see, you can right click on anything in your Hydroshare content and you can get a file URL and you can email someone or post someone if like, it's this file, I want you to look at that. You can put pictures here of graphics, anything you would want someone to look at if you were to physically walk into my office and show me something, which is not possible for many of you. The goal is we should be able to do this virtually.
All right, super cool.
Does anybody want to see more slides, or are we pretty saturated? I'm going to vote for saturated or asleep unless I hear differently, and tell you all to have a nice weekend. All right. Have a nice weekend, and post questions as they arise as you work through the homework.